Since the last video, the rest of the water in the vial has completely evaporated. This rapid evaporation may have been due to the environmental factor of being on a sunny windowsill. However, the crystals have not visibly grown in size since the last video. The largest crystal is still about 0.8 centimeters tall, and the crystals still cover about 40% of the inside edge of the vial. There is a slight film of precipitate on the bottom of the vial. If you want to grow one large, high-quality single crystal of alum, you could use a seed crystal, according to Seeding Crystal Growth 101 by Hampton Research. I would start by taking the largest, most uniformly shaped alum crystal from the ones that I've already grown in my vial. This would be the seed crystal. Then I would tie a line of fishing wire around the seed crystal and the other end of the fishing wire around a popsicle stick that I would lay across the top of a vial containing a saturated alum solution. I would let the seed crystal hang in the saturated solution of alum. A Kim wipe could be placed across the top of the vial to prevent impurities from entering the solution and polluting the growing crystal. Upon the seed crystal, the solute would precipitate and grow the crystal larger and larger, represented here by the dashed line. Suspending the crystal will allow for a large, uniform shape to form. In order to grow the high-quality crystal, one could cool the solution to allow the solute to precipitate. This would work because the process of crystallization is exothermic. The reaction between the aqueous solute and the solid crystals can be represented as this reaction, with the aqueous solute on this side and the solid solute, or the crystals, plus heat on the other side. By Le Chatelier's principle, in an equilibrium, if you decrease the temperature of an exothermic reaction, the reaction will proceed towards the side of the reaction where the heat is. In this case, decreasing the temperature would proceed the reaction towards the crystals and the heat, producing more of both. So if you decrease the heat, the reaction shifts. Despacing is very important for the identification of our crystal. The repetitive structural organization of a crystal's atoms can be described by a multitude of sets of parallel planes upon which the crystal's atoms are oriented. Despacing is defined as the distance between adjacent planes in one set of parallel planes. Despacing is crucial to understanding the spacing and angles of the many sets of parallel planes, which describe a crystal's unique structure. If scientists can understand the organization of the atoms in a crystal, they can determine the identity of the crystal. X-ray diffraction is a process that helps us identify the type of crystal we're experimenting with. Light is projected towards the crystal, and the light bounces off the different planes of the crystal. Between the planes is the despacing. So now, using the powder X-ray data for alum, we want to calculate the despacing for the most intense peak in the diffraction pattern. By Bragg's law, n, an integer, times lambda, the wavelength of the light used in the X-ray diffraction, equals 2 times the despacing times sine theta. N in this case is 1. The wavelength is 0.15418 nanometers. 2 theta, given to us by the graph, at the highest peak, is 20.7 degrees, so theta is 10.35 degrees. Plugging all of these variables into Bragg's law, we get that the despacing equals 0.42909 nanometers, and this is the space between the sets of parallel planes at the highest peak. In this video, I refer to Le Chatelier's principle, and the source for this is chemistrylibratext.org. I also reference Bragg's law and an X-ray diffraction chart provided to us by Professor Burns. I also discuss the fact that crystallization is an exothermic reaction, and the source for this is colby.edu, a report called Differential Scanning Calorimetry. Thank you for coming along with us and watching my alum videos.